All right, so hello everybody. My name is Casey Hines.
Myself, Atharva, and Wyatt couldn't attend this presentation due to a personal reason. So
Yep,
Casey will take forward from now.
yep. And so we did our group research project on smart cities and next generation utilities. So this is just kind of our agenda slide. It's kind of what we're talking about. So start with introduction, then move on to distributed energy resources, and then why they're important, then virtual power plants, advanced metering infrastructure, how advanced metering infrastructure is used in Missouri, and then to wrap it up, we're going to talk about the implications on Missouri and then references at the end. So smart city is one that employs a network of digital sensors, information controls, Internet of Things technology, and automation to create a system that improves the quality of life by reducing costs, creating a new and better services, improving sustainability, and helping the city grow and compete for business, institutions, and residents. So essentially, a smart city allows cities to be self-sufficient, meaning that they would supply their own power for this case, for the sake of this class, and then they all would also be independent from the overall grid. So they may have like one connection, just like in case of emergency, something happens, their grid goes down, they always have something else to rely on. But for the most part, they are like 100% independent from the overall grid. Also, a smart city allows or helps optimize city planning and also increases grid performance. And so through the use of the distributed energy resources, virtual power plants, and advanced metering infrastructure, this allows smart cities to be possible. And so we'll go on to the next slide, and Atharva will talk about distributed energy resources.
Thank you, Casey. So distributed energy resources are basically a small scale unit of power generation that operates locally and can be connected to a larger power grid at a distribution level. And basically, distributed energy resources is nothing but a microgrid, as you can say such. And some examples of these microgrids are solar panels, wind turbines, microgrids, and natural gas fuel generators. Moving on to the next slide. So the main importance of the use of microgrids are that they cut the cost for consumers as DERs reduce the length of transmission lines as we generate our own power near to a uh, location. So it reduces the transmission cost. Uh, they provide response in our peak demand, and they are sustainable and clean to use. Moving on to the next slide. Virtual power plants are nothing but, as you can see on the diagram on the right side, we generate a small amount of energies at a smaller scale and combine all of those energies at a principal VPP central, as you can see. And this energy is then transmitted uh, throughout the local. And if we have a surplus amount of energy, then we can even supply this energy back to the main grid. And the main difference between microgrid and virtual power plant is that microgrid can be confined, uh, has a confined network boundary, and can be disconnected from a larger grid to provide a like a self-sufficient power island, you can say. Whereas VPPs can stretch over a wider geographical area it can cover, and it can grow or shrink depending upon the market need or the real-time market conditions. So at the current time, since you all know there is a lot of demand for energy, and the best thing that we can do right now is bring our own energy on the table. So this is what VPPs can provide us all right now, and they, as I talked earlier, it reduces the transmission cost almost to zero, and it is a very economical and viable option for us right now. It can also help us reduce the CO2 emission, which can bring us closer in achieving the seven wedges that we all discussed in the class. And in our interview with Dr. Kevin Brannon from Evergy, he also projected that Kansas City would actually benefit economically if it chooses to go 100% renewable using VPPs. So Casey would be taking it from now.
So advanced metering infrastructure allows cities to set up better communications with their customer utilities, such as like electricity, water, and heating, in the forms of using smart metering. So smart metering, it allows customers to access their bills in real time in real time with their utility company. Additionally, smart metering allows utility companies to more accurately and easily read a customer's meter. So in the case of Missouri, everything is really spread out. So this would be, a useful technology to be able to use instead of having to send someone from the power company to each house to read the meter. And also they would let utility companies know more quickly if there's an outage at someone's house, or if the larger area nearby has an outage, or if there's any kind of energy theft. Another advantage of smart metering is that the grid operator can better forecast energy demand by seeing usage in real time. So whenever you're forecasting the power demand for the future, the grid operator can see, a year ago today, the weather was good, and so through the use of these smart meters, they can read the atmospheric conditions, and then they can give a better and more accurate reading and forecasting for the year to come. And then the in-home displays go hand in hand with smart metering. So in-home displays allow customers to see which one of their devices are drawing power, and this kind of gives them a better idea of what appliances are drawing power as well. And so one example of this, the reason that these would help or be helpful is that, let's say you have like a refrigerator on your network, and your in-home display can see the energy usage that it's drawing. You could theoretically turn your refrigerator off like overnight, considering you're probably not going to be opening it, so nothing would go bad. And then there you would save power since your refrigerator is like consistently running. So it just kind of gives you a perspective on what devices you might not think are drawing power, but they actually are. However, on the other side, that these smart meter devices require a lot of internet bandwidth. And so something will need to be done to increase the available bandwidth and internet coverage. So there's two different methods that we researched a little bit about that could potentially solve this issue. And the first one is broadband over power lines. So essentially what that is that internet companies such as like Fidelity is the local company here in Raleigh, could install their internet lines on like telephone poles and run them alongside of electrical lines. So instead of having to dig new lines, there's already existing infrastructure for them to attach their wires to. So that would help give more power or internet coverage, as well as using NANs, which is neighborhood area networks. So that's just kind of like having one large Wi-Fi router for an entire like city block, or a home area network, or HAN, which is just like your own little Wi-Fi router that you'd have in your house. And so how AMI is used in Missouri. So I read an article that said that recently Ameren, Missouri has a contract with Landis, GYR, for the St. Louis area. And essentially what their contract is that St. Louis wants to install more smart meters, and this Landis company is allowing them to use their MDMS, which is their meter data management software, to be able to actually run the meters and be able to collect data from them. But however, Missouri is not currently taking full advantage of these devices. A little more research that I found was that only like in the major cities in Missouri, so like Kansas City and Springfield, are really using these devices. And so this would also tie into being able to help meter reading in like rural areas. And so that kind of ties into our implications on Missouri. So Missouri is a rural state with about 29.6% of residents living in like a rurally classified area. And so the suggestion that our team came up with was to turn subdivisions into microgrids. So if subdivisions were placed on their own microgrid, then they would not need transmission lines running from larger or more populated cities. Again, they could always have one just in case if something were to happen. but in theory, they wouldn't need an outside connection to run their stuff. And this would also, in return, decrease transmission loss of power over like a long area or a long distance, and also would save companies money for not needing to install so many lines, if at all. So these microgrids would obviously need some on-site energy generation and storage. So you store them in large batteries, and you generate them by using solar and wind. So using renewable energy. And in addition to like having one main generation site, each individual homeowner could also install solar panels on their roofs, along with maybe like a small wind turbine, to provide their own power in case like something were to happen with like a blackout from that main transmission site. Then each home would still be able to power while they were getting it fixed, and they would also be able to in return store more energy in like the local battery to be distributed throughout the entire grid. And then, so combining the DERs, or distributed energy resources, virtual power plants, and advanced metering could help make Missouri's grid more efficient and resilient. So these independent grids would suffer fewer outages overall, due to them having their own generation on each house and as well as like the local grid. This would also help diversify Missouri's energy portfolio. So instead of only relying on coal and oil and other forms of energy or power generation, they would have more opportunities to use solar and wind. And then Missouri could also try to incentivize solar on homes, and which would in return help these microgrids be more efficient. And so overall, using microgrids and subdivisions could help Missouri's energy efficiency and lead a path forward to more renewable energy in the future. Are there any questions? That's the end of our presentation.